Okay, we're going to continue our lesson on H9E.2 matrix transformation, and we're going to talk about areas of an image. So prior to this, we've been doing stretches and enlargement and reflection and rotations, clockwise and counterclockwise. And fortunately, we've got these these formulas in our IB formula packet that will help us with that. So let's look at this first example in our handout from our textbook. So consider the triangle ABC with vertices 0, 0, 2, 2, -5. Show that the triangle is a right triangle and find its area. Okay, so the first thing I did is I drew it, and it looks like a right triangle. But the way you can do it technically is to look at the slope. So if I look at the slope of AB, we can see that it's got a slope of 1. If we look at the slope of BC, we see the slope is -1. And since the slope is the opposite sign and the reciprocal, well, the reciprocal of 1 is 1, we know that it's a right angle. Okay. Now, to find out the area, we know the area of a triangle is 1/2 base times height, right? So if it's 1/2 base times height, I need to figure out this length. Let's use a different color. That didn't really show up too much. I need to figure out this length here, and I need to figure out the height, which is, let's use green. Okay, that. So to calculate that, I said, okay, so the length from here to here is, I'm going to take the difference of the x values, which is 2, and the y values, which is 2. And so this length right here, from here to here, is square root of 8. And the distance from here to here, using the distance formula, I end up with the square root of 18. And so multiply these together, we're going to get square root of 8 times square root of 18 is square root of 144. And that is going to give me 12, and 12 times 2. This area is 6 units. Units squared. Okay. So now this triangle is enlarged by a factor of 3. Okay, so I'm going to draw our enlarged triangle here. And notice it says A prime, B prime, C prime. So it's very important that we put our primes on the upper right corner of our points here. Okay, in England they call that dashed. Okay, whatever, that's fine. Dashed, prime, whatever. Okay, so use matrix multiplication to determine the coordinates of A prime, B prime, C prime. Okay, so we know from our previous lesson and from our formula worksheet, if it's enlarged by a scale factor of k, it's going to be k0, 0k. So we've been told that it's going to be enlarged by a factor of 3. So instead of k003k, it's going to be 3003. Okay, and then the points 0, 0, I put that here in this first column. The point 2, 2, I put in this second column, and the point -1, 5, I put in the third column, and then I do my matrix multiplication. We always put the transformation matrix first, and then our image matrix second, and then we end up with our result. after the matrix multiplication, and with 0, 0, 6, 6, negative 3, 15, and that's how I got my points to draw my picture. Okay, and these are the coordinates. If you wanted to write this with the coordinates, you would just write 0, 0, 6, 6, negative 3, 15. Hit pause, replay if you need to see or hear that again. Okay, determine the area of triangle A prime, B prime, C prime, and what is the factor of, by what factor has the area changed? And by what factor has the area changed if it's enlarged by a factor of k? Okay, so the distance from A prime to B prime, so the distance from here to here, we know to the right I'm going over 6, and then I'm going up 6, right? So we can use the distance formula, which is kind of like Pythagorean theorem. This is 6, and this is 6, so I'm going to go 6 squared plus 6 squared gives me square root of 72. So that is this length of this green line. Okay, so now I want to figure out the length of this line here, right? So to figure out the length of that line, we know it goes over 9, and it goes up 9. So we know that this, using the distance formula, that's going to be square root of 162. And square root of 72 times the square root of 162 gives me 11664. Square root of that and divide it by 2, we get 54. So this new area is 54. units squared. And if we recall, this area is 6 units squared. So if I do 54 divided by 6, we could also say that this area is 9 times 6 units squared, right? So our first original shape was 6 units, and this is 9 times. This is increased by a factor of 9. Okay. Now here's the interesting part, the main part of today's lesson. So question C says calculate the determinant. Okay. So our formula for the determinant, if you may recall, I'm going to write this down here. So our formula for the determinant, if our original matrix is A, B, C, D, the determinant is equal to A times D minus B times C. So A times D is going to give me 3 times 3 minus C times B, which in this example here is 0 times 0. So my determinant is equal to 9. So it's enlarged by a factor of k. The area will increase by k squared. But the important thing here is when I take the determinant, we notice that we get 9, and the area happens to be 9 times bigger. So where we're going with this is our area of the image is going to be whatever the determinant is times the area of the pre-image. But we're going to show that in just through our lessons here. Okay, so we've got our first triangle here, 0, 0, 2, 2, negative 1, 5. Okay, this is the same triangle from the previous page. Okay, and we already know this area is 6 units squared, right? Okay. And we're going to undergo this transformation. So here's my transformation matrix. My image is 0, 0, 2, 2, negative 1, 5. Okay, and if I use my calculator and take the multiply these matrices together, I get 0, 0, 6, 2, 9, negative 7. And if I plot them, they go like this. Okay, so my new coordinates are 0, 0, 6, 2, 9, negative 7. Okay, now the next thing says show that the new triangle is a right triangle. So taking the coordinates, we know to find slope is equal to rise over run, right? Which is equal to y2 minus y1 over x2 minus x1, right? So using slope, I can say, okay, so 2 minus 0, right, divided by 6 minus 0, and I get a slope of 1/3. So the slope of this line right here is 1/3. Okay, the slope of BC, I'm going to say negative 7 minus 2, right, these 2 points here, divided by 9 minus 3, or 9 minus 6, and then we get a slope of negative 3. So since this is the opposite sign, right, this is positive, this is negative, and it's the reciprocal, I know that it's a right triangle. Okay, I can use the distance formula, and you don't need to memorize the distance formula. It's on your formula packet. I didn't put it on this review sheet, but it's in the formula booklet that you guys have. Okay, so if I use the distance formula, I find out the length of AB is square root of 40. I find the length of BC is square root of 90. And when I multiply those all together, I get that the area is 30 units. So this area here equals 30 units squared, which happens to be 5 times bigger than the original triangle. Okay. Part C says calculate the determinant of our transformation matrix, right? This was our transformation matrix. So we calculate the determinant of our transformation matrix. We get 1 times negative 1 minus 2 times 2. And I get negative 1 minus 4, and I get negative 5. And if I take the absolute value of this determinant, we get 5. So notice the determinant of the transformation matrix is 5, and the area of the resulting image is 5 times bigger. Interesting. Okay, so now we're going through a different transformation. Okay, consider the triangle with the transformation 2, 1, negative 1, 3. Okay, so here's the original triangle. We know that this triangle has an area of 6 units squared, right? Our old good buddy little triangle there, right? In fact, I'm even going to draw a little square because we know that's a right triangle. Okay. So, our transformation matrix times our original image, 0, 0, 2, 2, negative 1, 5. Just like the previous examples, We use our calculator, and we get our result image. Here, I plot the result image, and then I use the slope formula. I figure out the slope for this line here is 2/3. The slope of this line here is -4. This is not the opposite sign. Well, it is opposite sign, but this is not the reciprocal. So therefore, these are not perpendicular slopes. It is not a right triangle. Okay. So show that the area is equal to the determinant, the absolute value of the determinant times the area of the original triangle. So I take the determinant of this. So I have 2 times 3 minus -1 times 1. So minus -1 means plus 1. So 6 times 1, I'm going to get a determinant of 7. So I have 7 times my original area, which is 6 units. And now I have an area of 42 units. Okay. And so consider the transformation. Here's a third transformation. Does the relationship hold true? Okay, so if I multiply this transformation matrix times our original matrix, 0, 0, 2, 2, -1, 5, we end up with this result matrix. And if I find the slopes, I end up with the slope of AB gives me 3, and the slope of BC gives me 3. Oh my goodness, they have the same slope. So after undergoing this transformation, we see that these lines have the same slope. Okay, we didn't bother drawing this graph, but this does not form a triangle, because how can you have a triangle if two sides have the same slope? Now let's take the determinant of our matrix. I've got 2 times 3, right? 2 times 3 minus 6 times 1, which gives me 0. So if my area is the determinant times the original area, my new area is 0 units. Therefore, the relationship does hold true. The determinant times the original area will give you the area of the final shape. In this example, the area is 0. Ooh, ha ha ha! Perfect for Halloween. Okay, now this one here is explained in Khan Academy, but I'll make this brief. If we take the determinant of this matrix, we end up with 4. The area of this original rectangle is 7 by 5, which gets me 35 units. So if we multiply our determinant times this the original area, our new area of our bigger shape is going to be 140 units. You can hear this if you want to watch the Khan Academy. Okay. So find the area of the triangle. So now we're going to do some of the problems in the textbook. Find the area of the triangle with the vertices 0, 5, 4, 5, and 2, 7. Okay. So area of any triangle is base times height. So this base right here is 4 units. My height here is 2 units. So it should make sense that this area is 4 units squared. Okay. Use these results of the area image and the determinant of the transformation matrix to find the area of the images of these triangles. Okay, so we're going to do a vertical stretch with scale factor of 2, followed by an enlargement by a scale factor of 3. So the first thing I'm going to do, okay, after a vertical stretch, so the vertical stretch is this orange matrix. If this is happening first, it's going to be written here as a second thing. Okay, so the vertical stretch happens first, followed by an enlargement with scale factor 3. So the followed by matrix that happens needs to be written first here. Okay, so I do my matrix multiplication and my so the overall transformation after I've done my matrix multiplication gets me 3006. If I get the determinant of that, I get 18. And so 18 times my original area of 4 is going to give me our new area, which is 72. Okay. Now, what is the area after a transformation made by this matrix? Okay, so I find the determinant of this, and I get 16. So this transformation matrix is going to give me an area that is 16 times bigger. Okay, moving right along. Okay, prove that neither transformation changes the area of the determinant from a general matrix. So I'm just going to show. Okay, so if I do a reflection, okay, forget about math right now. If I do a reflection, I'm going to draw some shape. And if I'm going to do a reflection, okay, let's forget the happy face. Okay, if I'm going to do a reflection on this line, then I'm going to flip it over. Now, the question was, did the area change? No, this is still the same size if I'm reflecting it. The other one says about a rotation. If I've got a circle and I rotate it around, woo, woo, has this circle changed sides? No. Okay, now let's show this mathematically. Okay, so a reflection follows this transformation of cosine 2 theta, sine 2 theta, sine 2 theta, negative cosine 2 theta. Okay. If I take the determinant of that matrix, I end up with negative cosine 2 theta squared minus sine 2 theta squared, and then I end up with negative 1 times parentheses cosine squared 2 theta plus sine squared 2 theta, and this is the identity matrix, which is equal to 1. So the absolute value of negative 1 gives me 1. Okay, through a rotation, doesn't matter if it's clockwise or anti-clockwise, we use this transformation matrix. And same thing, when I take the determinant of this, I end up with cosine squared theta plus sine squared theta, which we know from our unit circle and from our formula worksheet that is an identity of 1. So because the determinant is 1, that means our area is not going to change. Okay, question 8. Let T be the linear transformation matrix. So here's my transformation matrix. The coordinates of the image of point P after undergoing this transformation. So here's my transformation matrix. Here's my point 1412. We do the matrix multiplication, and I end up with a new point here. The coordinate of the point having an image of this. So the final product, this is the result image, and we want to find the original image. Okay, the original image, we don't know. The result image is negative 12, 12. So in order to solve for the original image, I have to take the inverse of our transformation matrix times our result image in order to find our original image. Okay, you may want to hit rewind 3 minutes to watch this again if this was confusing to you. Question 9 is the same sort of thing. Okay, if it undergoes a transformation, here's my transformation matrix, here's my original image, and here is the result image. If I'm given the result image, I have to multiply the inverse of the transformation matrix times the result image in order to find the original image. Okay. This one was tricky. We did one exactly like this in our the H9E.1 handout, the handout just before this. We did one exactly like this. I think it was called example 8. I don't remember. So we are trying to find our transfer matrix A, B, C, D. We have point 1, comma 2, and it's going to, the result image of that is negative 1, 1. Okay, so transformation matrix, original point, original image, result image. Okay, so, and then I also have a point 1, negative 3, and the result image is going to be 4, 9. So I've got this matrix set up from 1, comma 2 to negative 1, 1, negative 1. I've got this matrix set up for 1, comma negative 3 to 4, comma 9. Taking this matrix, I could put it into an equation where I get A times 1 gives me A, B times 2 gives me 2B, and my result is negative 1. Here I've got C times 1 gives me C, D times 2 gives me 2D, and that is also equal to negative 1. Here I've got A times 1 gives me A, and B times negative 3 gives me 4. And here I've got C times 1 gives me C, and D times negative 3 gives me negative 3D, and that's going to be equal to 9. Now I'm going to take these two equations, or these four equations, to figure out what A, B, C, D are. So if I take this first row and this first row, I can use them together in order to figure out A and B. So I take the coefficients here. My coefficients are 1, 2, 1, negative 3, right? My variable matrix is A and B, and my the constants, or whatever it is, this final matrix here is negative 1 and 4. Now, in order to find out A and B, I need to do the inverse matrix of 1, 2, 1, negative 3. And I multiply that inverse matrix times negative 1, 4. And if I do that all in my calculator, I end up with 1 and negative 1. Same thing with my other matrix. So, oh, here's my blue pen. Okay, so I've got this line here and this line here, and together I'm going to set up another matrix. So my coefficients are 1, 2, 1, negative 3, right? The variable is C and D, right? And the result there is negative 1, 9. So in order to calculate C and D, I take the inverse matrix of the 1, 2, 1, negative 3, and I multiply that times negative 1, 9. And then my transformation matrix gives me 3 and negative 2. So my overall transformation matrix is 1, negative 1, 3, negative 2. Okay. Okay, this is pretty important. I think question 11 is critical for understanding what we're doing. So we've got this triangle. We're going to talk about those points a little later. Okay, we're going to go through a rotation clockwise about the origin, and then do a reflection. Find out the transformation matrix that represents the rotation clockwise and the reflection. So if I've got these 2 points here, okay, see those 2 green points, and if I'm going to rotate it clockwise, so I'm going to put my pen here and rotate it clockwise, you can see where the new points are going to land, right? This this pink point lands there, this blue point lands there. So if I'm looking at my original one, which is 1, 0, that's going to end up at 0, 1. This is 0, -1. Sorry, my mistake. And then this pink one, which is at 0, 1, its new location is going to be 1, 0. So this is my transformation matrix when I rotate something clockwise 90 degrees. Okay, if I'm going to reflect on the line y equals -x, this point right here, 0, 1, the new point here is going to be -1, 0. Oops. And if I take this point here, 1, 0, the new point is going to be here at 0, -1. Okay, and so when I reflect it on the line y equals -x, that's where it's going to be. So find a single matrix that represents R followed by T. So if it's R followed by T, oops, yikes, I hope that didn't mess in it. Okay, if I'm doing R followed by T, that means if I'm doing R, I'm going to do this one here first. Okay, followed by T. If it's followed by T, I'm going to write matrix T before this one. It's kind of confusing to think about that. Okay, so if I'm going to write this as a single matrix, oh, I guess I didn't do that. So let's do that together. I have 0, so I'm going to multiply this row times this column. So 0 times 0 plus -1 times 1 times -1. To get this 1 down below, it's -1 times 0, which is 0, and 0 times -1, which is also 0. Okay, so to get this one, this next space right here, it's going to be 0 times -1 times 1 times 0. So that's 0 times times 1 is 0, and -1 times 0 is 0. And then to get this bottom thing, it's this row, this bottom row, times this column here. So -1 times 1 is -1, and then 0 times 0 is 0. So the result matrix of multiplying this by this gets me 1, 0, 0, -1. Okay. So hence, find the image of the triangle after both of these transformations. So I'm going to use this transformation matrix, TR, and multiply it by these points here, which is 1, 1, which is why I've got 1, 1 here, 3, 1, so I got 3, 1 there, and 3, 3, which is we got a 3, 3 there. So I multiply those matrices together, and I get this. Okay, so I'm going to sketch. Let's talk about what happens. Okay, so what's happening here is best explained with a picture. Okay, here is my original matrix using the original points. Okay, so what did we say was happening? The first thing that's happening is it's rotating clockwise 90 degrees. So if it's rotating clockwise 90 degrees, that means, let's watch this happen. Okay, so it's going to twirl next 90 degrees this way. Do, 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 do. Okay, so now this has twirled 90 degrees clockwise. Okay, and then now what? Now we're going to okay. Well, this line didn't show up very good, but that's okay. So we're going to reflect it on the y line, y equals negative x, and you can kind of see what's going to happen. If I reflect it on that line, now it's ended up there. So it really looks like it's just reflected, looks like reflection on the x-axis, doesn't it? All done. Fast forward, rewind, see the parts you need to see if you need extra.